Hello, everyone. Welcome to Metcalf Institute's 26th Annual Public Lecture Series. I'm Sunshine Menezes, Metcalf's Executive Director, and I'm joining you today from the traditional homelands of the Narragansett and Niantic nations. Their lands and waters originally encompassed what is now the state of Rhode Island into eastern Connecticut and southern Massachusetts. We honor and respect the enduring and continuing relationship between the Narragansett and Niantic peoples and these lands and waters by learning more about their history and present-day communities, and by becoming stewards of the land we too inhabit. And that is why we want to talk with you about a variety of innovations in how to produce a clean energy transition. The University of Rhode Island's Metcalf Institute has been advancing informed and inclusive public conversations about science and the environment since 1998. We achieve this through science training for professional journalists, communication training for scientists, and public events like this one. We also founded the Inclusive SciComm Symposium, which brings together researchers and practitioners from across the country, and in fact, around the world, to make all types of science communication more inclusive and equitable. This year's lecture series explores some of the opportunities and challenges of creating an equitable transition to clean energy. So far in this series, we've heard about spatial planning approaches to ensure environmentally and socially sustainable solar and wind development, equitable interventions in the transportation sector, and the major infrastructure shifts needed to get us through what Dr. Emily Grubert calls the mid-transition period. Today, we're excited to hear from a panel of experts who are pursuing a range of innovations that can accelerate our efforts to decarbonize. We thank you all for being here today to begin exploring this critical topic with us. I also want to note that, thanks to several generous donors, Metcalf Institute has a dollar-for-dollar matching opportunity this month until June 30th for all donations up to $12,500. Your gifts support public programs like this one, as well as professional development for journalists and scientists, all in the interest of advancing conversations that increase awareness and action on the urgent challenges posed by climate change and environmental inequities. If you would like your gift automatically doubled, please click on the link that is now in the chat. And now to today's lecture. It is my pleasure to introduce Jeff St. John, Director of News and Special Projects at Canary Media. Jeff covers technology, economic, regulatory, and social justice issues pertaining to the global transition to low carbon energy, with a particular focus on the electricity, transportation, and building sectors. Jeff earned a master's degree from the University of California, Berkeley Graduate School of Journalism. He is the former managing editor and senior grid edge editor of Green Tech Media, and previously reported for the Fresno Bee, the Tri-City Herald, and the Anchorage Daily News. He's gotten around. His areas of expertise include renewable energy, smart grid, distributed energy resources, energy storage, demand response, and electric vehicles. And he is therefore the ideal person to guide us through a conversation with today's panelists, whom he will introduce. Welcome, Jeff St. John.
Thank you very much, Sunshine. I didn't know you were going to read my whole bio, but that's great. I appreciate it. And thank you to the Metcalf Institute for inviting me to moderate this panel on some of the less commonly discussed technology and infrastructure solutions that we need to scale up to achieve the transition to clean energy. I think the basic framework of this discussion is, long story short, everyone's talking about solar and wind and power and lithium-ion batteries and electric vehicles and heat pumps and decarbonizing and electrifying buildings. But the transition to a truly zero carbon energy system is going to require a host of less well understood technologies to be deployed at hitherto unprecedented scale. And it's going to require a really unprecedented level of coordination and collaboration and innovation between government and private sector and different sectors of the energy infrastructure we have today. And it's a lot of work ahead, and it's actually very exciting stuff. Luckily for us, we have three experts here today to talk about their work on these vital intersectional solutions. And let me introduce them. First, we have Gia Schneider, CEO of Natel Energy. And Gia co-founded Natel in 2009 with her brother, Abe Schneider, with the goal of making fish-safe hydro turbines. This is really important given that hydropower is the country's largest carbon-free electricity resource and is renewable. And Gia leads and operates Natel's portfolio of hardware and software water solutions, which include fish-safe power engineering, oversight of hydropower project developments, river restorations, and remote water sensing and forecasting through the company's Upstream Tech brand. And Gia, welcome. Thanks very much, and look forward to hearing more about Natel Energy and what you're doing. Second, we have Ramya Swaminathan. Ramya is CEO of Malta, a company that's developing a novel technology for long-duration energy storage. Long-duration energy storage is really going to be vital as we scale up to a majority and then entirely clean or carbon-free renewable energy on the grid. And it's quite challenging. There are a lot of different technologies that can suit that purpose. Ramya has developed Malta from concept to commercialization, leading its spin out from X, Alphabet's moonshot factory, formerly known as Google X, back in 2018, and has led its ongoing work on deploying the technology and developing it for scale up and deployment in the field. And she's also a former hydropower and pumped hydro storage executive, which I think is an interesting linkage to be made with the work that Gia is doing. And finally, last but not least, we have Dr. Ben Kroposki, who is the director of the Power Systems Engineering Center at the National Renewable Energy Laboratory in Golden, Colorado. Ben leads NREL's strategic research in the design, planning, and operations of electric power systems. He has over 30 years of experience in the design, testing, and integration of renewable and distributed power systems. And he'll be able to help us understand the challenges and the solutions being developed to achieve a high renewables energy system, including some of the technologies our first two panelists are going to be discussing. Welcome all, and thanks for joining us. We are really looking forward to fielding audience questions for our experts. Please use the Q&A feature at the bottom of your Zoom screen there to submit those questions, and we'll be taking them up later in the hour. But let us begin by giving each of our experts a chance in turn to talk about what they and their companies and organizations do and why it's important. And if you don't mind, Gia, would you like to take the lead here?
Absolutely. Thanks very much. It's a pleasure to be here with you and everyone else here on the panel. Let me share my screen, and I will go through a few slides to talk a little bit about what we are doing here with sustainable hydropower and design of fish-safe turbines. So we at Natel are very focused on hydro, in part because it is that the world's largest source of renewable energy today. It's actually the third largest source of electricity generation in the world today after coal and gas. In the US, it's a critical part of how we maintain a reliable grid as we scale production of intermittent renewables. I think that's kind of a couple of facts just to ground us for the discussion, are that somewhere between like a megawatt or a megawatt hour, a unit of hydro supports integration of somewhere between 3 and 5 megawatts, megawatt hours, again, unit of generation of intermittent renewables. And that's a really critical thing to pay attention to as we think about the value of flexible generation resources and that the role that those play in allowing us to maintain a reliable grid as we drive deep decarbonization. And hydro is quite key to that. Some other facts that are really important are that while we have 1.3 terawatts of installed capacity today in hydropower, there are two very important challenges ahead for the industry. One is for the existing fleet. About 40% of that existing fleet is quite old and is facing the need to upgrade. New equipment, new turbines, et cetera, needed in the next decade or so, or else we will start to lose some of that existing generation. That's about that 476 gigawatt number. And then in addition, in order to hit kind of target, climate targets to keep to limit temperature rise, we really need to almost double the installed capacity of hydro over what we have. And we need to do that here over the next couple decades pretty quickly. So the question we're focused on is, how do we do that? How do we enable that maintenance of the existing fleet and growth of new, but do so in a way that is truly sustainable? Because we really, deeply think that the future of hydro has to be sustainable as we think about both, again, new build and upgrades of the existing fleet. So when we think about new build, one approach that makes a lot of sense is to think about, going to more distributed systems that are designed in ways that help improve or help maintain, in some cases, maybe help improve river connectivity. So there's some really interesting work looking at dam removal, dam reconfigurations, et cetera. And that we think is an important first part of the process. So how do we think about reimagining that from a civil works perspective? Where we are really focused, though, is how we can change the prime mover. So the thing that's core to every single hydropower plant, that is what, moving water turns to produce electricity, which is that unfortunately today, 1 in 5 fish that on average that go through a conventional turbine don't survive. And we really need to turn that around if we're going to do, in addition to tackling the climate crisis, tackle the biodiversity crisis that we face. And so our approach to this has been to design a new type of turbine called the Restoration Hydro Turbine, or RHT. And the RHT embodies in its design several really important elements in the blade shape that allow it to maintain high performance and be fish safe. We've done a ton of testing. So passing, what you can see here is videos from 3 different tests that we've done using trout, eel, and alewife. Just 3 of a whole range of tests that we've done with third parties that have been able to demonstrate 98 to 100% safe passage of a diverse set types of fish through very extreme operating conditions. In many cases, we're operating at speeds that are 400 to 600 RPM, for example. And this is critical, just again, to the goal of being able to simply allow moving water to pass through a turbine, fish can pass through safely, and still generate electricity at a high performance level. How this comes home, just zooming in here to the US, really focuses on that existing fleet, question, the fact that we've got a large existing installed base. And if you look at where we have existing installed hydro today, represented by the blue circles, what you can see is there's a very strong overlap of existing hydro with critical fish populations. And this we see represents this very substantial opportunity, given the fact that the US fleet is over 65 years old on average, for us to do these upgrades that maintain, or in some cases improve, power generation from existing assets and take survival from something that's fairly marginal to survival that's near 100%. Digging in a little bit more detail, like kind of the near-term opportunity is that in addition to the fleet being old, in addition to having that overlap, we've got a lot of projects up for relicensing in the next decade or so. Again, strong overlap with where we have sensitive fish populations that we're really focused also on recovering. Last point that I'll note here is that, of course, interconnection is key to enabling this transformation of our grid. That's another area where I think hydro has 2 really interesting characteristics. Again, just zooming this into the US. One is that hydro as a grid resource provides a full stack of reliability services on par in most cases with natural gas. And that's important, again, for maintaining reliable grid. The other is that because we have this large existing installed base and we have this real opportunity to upgrade it, get in some cases 5 to 15% more out of the existing assets that are already interconnected, there's again this really interesting, very critical near-term benefit that we can see that while we also have to build a lot of new generation, interconnection is a process that unfortunately is lengthy and time consuming. So hydro plays a really interesting role in how we think about navigating this, looking out over the next couple decades. So really appreciate it. An opportunity to share a bit more. Happy to answer questions as they come up.
Wonderful. Thank you, Gia. And I should know that I want to thank Gia for inviting me over to Natel's site and my hometown of Alameda, California, and getting to see those turbines in person in their test environment. It's fascinating stuff, and how the fish make it through at those speeds. The hydrodynamics, really, really fascinating, important stuff. So thanks for sharing. I have not yet seen Malta's technology, but Ramya, I would love to ask you to tell us more about how Malta has developed its particular flavor of electricity to thermal to electricity long duration energy storage, as well as some insight into why long duration energy storage is such a challenging yet vital piece of the future clean energy puzzle.
Absolutely. Thanks so much, Jeff, and look forward to the discussion. So I also am going to share my screen here, and hope you all can see that. I think maybe I'll just make some introductory comments that can be very limited, right? But we are in an absolutely critical time with respect to climate transformation. And this, I think, is outdated even now. And so, what we see is that we're in a place where we're what the IPCC is calling code red. And the gravity of that situation is actually intensifying as new data come out. The optimistic and remarkable fact is that wind and solar are now the cheapest form of generation. And the largest contributors to GHG emissions, now these are different units, they're from different sources, but generally speaking, what you see is that electricity, decarbonizing the electricity stack, is absolutely essential to ultimately decarbonizing kind of the overall contribution to carbon emissions. And in order to do that, Malta's thesis is that you can't do that without long duration storage. So let me explain why that is the case. So this actually comes out of a modeling study that was based on Minnesota, but in general terms, I think it's broadly applicable to a variety of grids. So I said that wind and solar are now the cheapest forms of generation. So let's take a look at how we might construct an electricity grid. And actually, we're going to start with load. Electricity demand is what's here in red. And what you see is, broadly speaking, it's going to be pretty predictable. There's typically an evening peak. These are days. And so towards the end of a day, you see a peak as people come home from work. And there's a lot of electricity demand. It goes down overnight and then starts again ramping up during the day. Let's add to that hydropower. So a predictable, broadly speaking, flexible asset that can really form a renewable resource, but has many of the characteristics of baseload power. Let's add to that then, on top of that, solar. And what you see is that solar, like demand, is somewhat predictable, typically, which is that the sun rises every day, thankfully, and sets every day, but it is offset from demand. So your peak solar generation typically does not happen at the peak demand time. And then let's add to that something pretty unpredictable, which is wind. So in this particular modeling example, what you see is that you've got several days of pretty low wind production and several days of extremely high wind production that in fact exceeds demand on those days. And what happens in those cases is that you see two areas of problem. You see wasted energy, what is typically curtailed. So essentially, since the grid has to always be in balance between supply and demand, any production that is over demand is essentially wasted. It's curtailed. But you also see an issue here where you've got a gap. Your demand exceeds the supply that is available from renewable resources. And what we do today is typically to fill that with fossil fuels. And so what does long duration storage do? Long duration storage, in general, all long duration storage, essentially takes all this energy that's available during surplus times and time shifts it to times where its marginal value is very high. And all storage does that, and all long duration storage does that. And typically what you'll see in this example is, this is a period of, call it 4 days that need to be covered. So our thesis is that in general, there's an equation that will make renewables work as the solution to the grid. This is already true. The price of renewable energy, depending of course on location and the resource endowment, is already lower than the price of a carbon intensive energy source. What we ultimately need will be that the price of renewable energy plus the price of storage will be less than the price of carbon intensive energy sources. And what you see is that the DOE has strongly kind of stepped into and placed its weight behind this goal, which is to drive the cost of long duration energy storage down by 90% through the Earthshot initiative. So those are sort of general remarks about long duration storage. Let me just frame Malta for a second. So like all long duration storage, we enable the shifting of renewable energy from one period of time to another. Our sweet spot is 8 hours to 8 days. We are operating in a grid scale environment, so we're really looking at 100 megawatt type scale. Thermal storage, I'll talk about that in just a second. And we have technically and commercially mature components. A critical piece of what we offer, actually Gia referenced as well, which is the need for reliability assets on the grid, particularly in an environment where we're adding a lot of intermittency through wind and solar and a lot of inverter-based resources. And what Malta does, not only in physical looks and feels very much like a traditional asset, but its operability is also modeled on that of a combined cycle gas plant. And we use many of the same components that are used in traditional fossil assets. So critically, to the grid, Malta looks and feels very much like a traditional fossil asset, which provides reliability services and most significantly, real rotational inertia, which maintains frequency support on the grid through the use of large spinning mass on the grid. A critical point to consider in the context, particularly of the Metcalfe Institute and the framing of this entire lecture series, is about the just transition and the ability to bring along workers who would otherwise be displaced by the energy transition. I've already said that the Malta plant looks and feels very much like a traditional fossil asset. A critical component of that is that it uses the same skills to construct, to operate and maintain as traditional fossil assets. So workers who, for example, would be displaced by the shutting down of a coal plant can very much be integrated into the operations and maintenance of a Malta plant. And we're actually finding a fair amount of resonance with customers who are looking to make some of those transitions with their fossil-based assets, but the displacement of workers poses a real issue to them in advancing that transition. So with that, I'm going to stop sharing and very happy to participate in the conversation and answer questions.
Wonderful. Thank you very much, Ramya. And we've just heard two examples of long duration storage and kind of basically clean energy assets that can maintain a reliable supply of power for times at which our intermittent or variable clean energy resources, the solar and the wind, need them the most. I would love to invite Dr. Kroposki to the virtual stage now to talk a little bit about how the kind of grid itself and the underlying kind of infrastructure of markets and grid operations are evolving or need to evolve to be able to integrate these kinds of services into an increasingly high renewables environment. Ben, please take it away.
Okay, thank you. And great to hear those previous talks because they really laid sort of the foundation of parts of the entire system that are going to be needed as we move into the future. But we're undergoing a significant transition in the energy sector and the power sector right now. We're moving from a power system that's been around for over 100 years. It's transitioned to something that was based primarily on coal and natural gas. But what we need to do is try to transition again to 100% clean electricity sources. So that would include things like wind, solar, hydropower, and nuclear power. all of these potentially are clean energy sources. But as we make this big transition, there's a lot of things that really need to change and update. And one of the other big things that's also happening is if we take the energy sector as a whole, we need to think about other things that traditionally haven't been electrified, like the transportation sector, vehicles, as well as heating and cooling systems and industrial sectors. And how do we transition all of those to carbon-free sources? Well, one of the big ways, and we've kind of talked about this a little bit, is that we need to electrify practically all of those things as much as we can, because if we can electrify most of those loads and have the power system then transform to a decarbonized power system, that will get us a majority of the way to an entirely clean electricity or energy sector. So there's a variety of challenges for this transformation, and people around the world are working on solutions to this. But I'll, at a very high level, talk about some of the particular challenges with making this a reality. So first off is the amount of wind and solar that is going to be needed to be deployed. If, as you heard the talk from Malta, wind and solar are now the lowest form cost of electricity in the United States for most of the continental United States. The challenge really ends up being that those are variable sources. So how do you deal with that variability? The other thing is the amount of wind and solar that needs to be deployed. Since wind and solar are only producing electricity certain times of the day, the capacity factor, or when they're actually producing, is going to be much less than if you compare that to, say, a nuclear power plant that may be running at 90% of the time. Wind and solar probably are only going to be running, say, 20 to 30, 40% of the time. And to make this giant transformation, at least by 2035, in the next 15 years or so, we need to basically install roughly 10 to 15 times the current amount of wind and solar across the United States. And then to get to the full energy system transformation, it'll be much larger than that. To handle that type of deployment of wind and solar resources across the US, we also need to look at expanding the grid. So how do we expand the transmission system and the distribution system to accommodate all of these different types of resources that'll be generally spread a little bit more across the United States instead of large central station plants like we currently have. In doing so, in expanding the transmission grid, there are several technologies that need to be looked at there, including the use of high voltage DC transmission lines, better interconnections, and better routing of power systems. As we get back to thinking about flexibility to accommodate the variability with wind and solar, there's a variety of things that need to be better understood around that. So this would include things like existing generation. How flexible are they? How fast can they ramp up and down? Here's a great example where hydropower really can come into play, because you can do very fast ramping of hydropower systems. They really map well to and complement wind and solar variability. As I mentioned, expanded transmission can also help with that variability that you see in wind and solar by allowing balancing areas around the country to generally share power. We can improve things like forecasting of wind and solar. We can add controllability of loads much more than we do now. And that could be especially relevant as we think about the transportation build out of electric vehicles. If we could turn charging on and off in respect to when wind and solar is available, that really would create a lot of flexibility in the existing grid to accommodate both the load growth from electric vehicles, but also that variability from wind and solar. And then also, finally, energy storage is going to be critical as we think about really large scale deployments of wind and solar. Currently in the United States, we have on the order of around 23, 24 gigawatts of energy storage. Most of that is pumped hydro. But if we look into these future energy scenarios, we're going to need on the order of 10 to 20 times that amount of capacity of energy storage. And we're going to need a variety of different technologies to provide that scale of energy storage for wind and solar. And finally, the one last thing I want to mention involves around wind, solar, and battery technologies. We heard a little bit about the fact that these are inverter-based technologies. That means they're based on power electronic switching devices. They don't typically have a large rotating machine inside of them, a synchronous generator. And we need to make sure that these inverter-based resources are also able to provide a variety of grid reliability services at any level. And so we're working right now, I actually am leading a consortium looking at grid forming inverter controls so that we can actually run grids of the future with up to 100% batteries, wind, and solar to make sure that those maintain operational stability at any condition. The one last thing I would like to show is just show one little screenshot here of what a future energy grid actually would look like. And you can see from this diagram here, again, as we mentioned earlier, to run the grid at any level, you need to balance load and generation at every time scale. This is showing you the US, and this little line that's coming across the screen is the sun coming up, and all the yellow that's appearing on here are hundreds or thousands of solar plants. The blue in the middle of the country is kind of wind. The lighter blue is hydropower plants. The red is nuclear. And this is a day in the life of a future grid that's got massively deployed wind and solar, and the power flows that need to happen, those are represented by those arrows between different areas around the country. And as things happen, like the sun will set here in a second, you'll start to see another line come across, and all the solar needs to be backfilled with some other type of source. In this case, the green is representing natural gas, but you could think about that being replaced by larger amounts of energy storage or green hydrogen-powered gas plants. But this is an idea of the fact that, yes, we've done enough studies to show that these future scenarios with this massive deployment of variable resources are possible with things like transmission expansion, larger scale deployment of energy storage, and a variety of other techniques. So it's all doable. It's a matter of actually getting this up and running as quickly as possible and having this clean energy system of the future turn into the reality that we're all pressing forward with. So with that, I'll stop and we can take questions from everyone. Thanks.
Wonderful. Thank you, Ben. And I would love to know if you guys are making that graphic available for use by journalists, because I think it could be really useful to show to people, and including maybe prospective new transmission lines, or perhaps new storage capacity that maybe fills in for some of those nat gas power plants.
So I'll just say yes, those are available, as well as you mentioned transmission expansion. I'll just, I didn't mention, but both NREL, National Renewable Energy Lab, and Pacific Northwest National Lab are working with the Department of Energy right now to develop a national transmission plan for transmission corridor identification across the continental United States. That should be becoming more public here later this year with the rollout after we're done reviewing the outputs of those models and with stakeholders. But that's something that's coming, is to think about how to most efficiently build out the transmission grid in the United States.
Great, thank you. Well, thanks to all three of our panelists. And we do have some audience questions rolling in, and we do want to get to those, but I thought I might ask all three of you real quick. I think one of the reasons that these topics don't necessarily get as much attention as wind, solar, electric vehicles and the like is because they are seen as having longer time scales to development ahead of them. And I suppose that we all focus more perhaps than we ought on the short term. But I also know that the kind of groundwork that's going to be required to enable technologies like those being developed like Natel and Malta to gain kind of commercial viability requires, there's a lot of work that needs to be done today to make that possible in the future at the time that we need it. I don't know if the three of you might have some thoughts about where you see the work being done today that is laying that groundwork for enabling these technologies to take their needed place in the power systems of tomorrow or 5, 10, 15, 20 years from now, as well as what work is perhaps not being done at the scale or urgency required. And feel free to jump in as you wish.
So I'm happy to offer a few thoughts here. I think a remarkable thing that is happening today is the fertility of the innovation sector in clean tech. And I think that is not limited to any one sector or one technology, right? So it's not, it certainly is storage, but it's not limited to storage. It's different kinds of generation. There's work being done in hydrogen electrolyzers. There's a huge amount of vibrancy that is bubbling throughout innovation and technological innovation in particular. And I think that is a remarkable thing that we should all be very appreciative of. So I think that's definitely a place where you see a lot of activity. I think in my view, there are a couple of challenges that we collectively really need to key in on and do a better job of addressing. And in my view, there are really two things. One is market design. So a lot of the barrier to the more widespread adoption of many technology, I'm going to talk about storage here, but I think it's not limited to storage, but is the fact that the market regulations, not only here in the United States, but largely globally, were architected for a legacy system. And so I can give you a couple of examples, right? Typically, the old system was architected for things that function like loads and other things that function as generators. And if you look at storage, it's both. Right? You charge as a load and then you generate as a generator. And so you're really crossing these two silos that largely are governed independently. Similarly, in many jurisdictions, transmission and generation can't really own each other. And storage can function as both. And so in market segments where that joint ownership is prohibited, or you can't really realize revenue across both of those categories, that forms a significant inhibitor to the adoption of storage. So that's kind of one critical point about market design. I'm sure there are a lot of other examples that are not just limited to storage. The other thing, in my view, that really needs solutions is that for technology to be commercialized at scale requires a lot more than technology that works. So I actually think that technology working is not our issue. I think we have a huge amount of technology that is broadly proven, broadly works. And I see Gia nodding her head, and I'm sure Natel is in that position. I think Malta is. I think there are a lot of other companies who have technology that works. There are, for widespread commercial adoption at the scales we need for the energy transition, a lot of the gap in the white space is about funding for first of a kind or early commercial scale, very large scale installations. It's for commercial features that are not typically covered by just venture funding. For example, full EPC wraps, indemnifications for tax equity, the kinds of security and credit worthiness that you need in order to post the kind of security that commercial market participants are looking for participation in tenders, bids, RFPs, proposals, interconnection, et cetera. And all of those are really end up being stumbling blocks, real blockers to technological innovation, making it to market at scale. And that's not really a technology risk. That's not really a technology problem. It really is kind of a commercialization problem. And I think it needs to be addressed as different from funding for technology.
Yeah, I would just add a little bit further. I think I agree on the signs of positive signs and progress. I also maybe would just add a detail to that, which is that between the infrastructure bill from 2021 and the Inflation Reduction Act from 2022, we actually have like an enormous amount of public funding on a whole host of levels, everything from pure concessionary funds to to debt and debt supporting structures that are super important in helping to drive the industry forward overall. So that's super positive. I think in addition to the market structure and also still yet gaps on the financing side that Ramya identified, a big issue right now is interconnection. That I think is something which, just as a statistic there specifically, there's something like it's estimated somewhere between 5 and 10% of the current total renewable energy projects in the interconnection queues across the United States today will ever be built. It's the kind of, you can find different estimates, but it's a small percentage. We have enough in the queue, actually, that is something like 2 times the total installed base of generation in the United States today. So we have this massive number of projects that are proposed in interconnection queues. A tiny fraction of them are going to get through, and you have to ask the question why. And in addition, not just why will only a small fraction, but also, unfortunately, the time frame, because time is a critical factor at play here when we think about the transition in this context of climate change, has just expanded. We're seeing queues now in PJM and MISO that are 4, 5, 6 years to get through. And so I think that is an area where it's a known issue. It's one where folks are trying to figure out how to make progress on this, but it is a real major stumbling block, and it cascades back up the food chain, if you will, to deployment. Because at the end of the day, for project finance, before you even interconnection, having approval to interconnect your project is a critical commercial step in having certainty that you will be able to actually see revenue from your project. Until you have an interconnection agreement, you are entirely uncertain as to whether or not you will make money from building your project and selling it. And if it's going to take you 6 years to get your interconnection agreement start to finish, well, guess what? You now have 6 years of work that you have to finance that's not financeable by project finance, that has to be financed in different ways with higher risk capital in a highly uncertain environment, that now you have to fund. And that, again, kind of circles back again to Ramya's point. So I think it's interconnection is this multifaceted stumbling block in the process right now that we have to figure out how to solve.
Yeah. Now, Ben, I don't know if it's fair for me to ask you to solve all the problems that Ramya and Gia have just raised, but I am curious about how NREL's work might be kind of looking at ways in which you can inform discussions and work around reforming or evolving new market structures to support, long duration storage or other resources that don't have, kind of recognized value necessarily in energy markets. Right. And if you got to solve to interconnect, I'll take that too.
That one's tougher. I will say that there is definitely a lot of discussion on both of those topics right now, because they're kind of key to making this happen. If you step back and realize, like, we have these goals of getting to 100% clean energy system by 2035, that's only 12 years away. And if your interconnection queue is telling you that you can't even get stuff installed for 5 years, how are we ever going to make these goals? So there's definitely something that needs to happen in that space. At NREL, we are looking at, let me step back and talk about markets, trying to work with again, it's an interesting pinch point on both of these problems. Markets are driven by, in the United States, unfortunately, we don't have one market rule. There's lots of different markets, but in general, the ISOs and RTOs that run the markets are starting to think about how to accommodate this variability in generation and provide incentives there. But the challenge we have is there's not a big incentive today to give you a market for something that you need really 5 to 10 years from now. And so how do we make sure that markets are moving in the right direction to enable these new technologies that are providing a variety of services that today somebody's meeting with a natural gas plant, but in the future we want to meet with other newer technologies. We are looking at NREL at a variety of different market mechanisms and then working with the ISOs to help them implement it. But at the end of the day, the ISOs and regulators make up those market rules that move things forward. And the interconnection queue challenge is agreed, a huge big issue that has appeared here recently, I would say, because people are like, okay, we see what we need to do. We need to get this stuff deployed. First step in getting deployed is make sure I get an agreement with where I want to interconnect on, and that a bunch of people jump online, you get it, you fill out your interconnection queue request, and now you end up, I just was looking at the ERCOT queue yesterday for a different project, and you have 1,000 projects in that queue that total up to twice as much capacity as the whole peak load of ERCOT. Awesome if they could all get installed and interconnected, but I think a lot needs to be figured out about how do we get these things moving much quicker. So can we come up with ways of doing system-wide studies and analysis to get those approvals from the engineers that are looking at individually right now this particular plant? The problem you have with doing that is you have all this uncertainty. If you look at plant number 1 versus plant number 10 when they come online, seems
Right.
like something though that we could put some resources behind to get figured out to move those ahead quicker. So unfortunately, those are really tricky problems to get solved, but something that we do need to do if we think we're going to meet any of these goals for
Absolutely.
clean energy systems.
Great. Thank you for fielding that insanely complex set of questions. I know our audience has some questions, which may be a little bit easier to answer. I wanted to jump to the first one, and this is directed to you, Gia. An audience member is curious to know if in North America, if there are any tidal hydropower projects underway, that being, I guess, you're capturing the tide when it's high, and then running it when it's low through a turbine. Curious if this is something.
I mean, there are so people are definitely have looked at tide systems in some of the places where you do have very high tides, typically a little bit further northern latitudes. At this point, I'm not aware of any substantive of that kind of a conventional barrage tidal projects of substantial size. There are some in Europe that already exist and have been operating for quite a number of decades.
Mhm.
There are folks looking at hydrokinetic, which is where a tidal system that is just installed in the current in places where you have high currents, but not barrages. And there's also a lot of folks looking at things around ocean power, wave power, etc. So there's interesting things happening for sure. And maybe the one point I will note, I think in general, there's been a gradual move away from classic barrage tidal power simply because of the fact that the environmental impact of them is quite substantial. You end up creating a standing brackish pool that completely wipes out the ecosystem of that tidal zone. And I think given the particular sensitivity and value of ecosystem services that often those types of tidal zones provide in terms of water quality, for example, in general, the total cost benefit trade-off has tended to shift away from like a classic barrage system. And so folks tend to be a bit more focused on some of the hydrokinetic, current, et cetera, options
I see.
right now.
I see. That's an important point. Thanks. Ramya, we had a question from an audience member regarding the possible interaction of Malta's technology with a combined heat and power system, which I think is an interesting question. I guess if you're storing heat to turn into electricity later, maybe that heat could
Absolutely.
something else. And don't know if that's part of your plans going forward.
It very much is. So if I could just maybe take a 30 seconds to describe the technology a little bit. So
That was a question too. So thank you.
So essentially, Malta's technology is a heat pump on the charge side and a heat engine on the generation side with thermal energy storage in the middle in the form of molten salt on the hot side and just a commodity antifreeze fluid on the cold side. And it's the delta between the hot and the cold that drives the efficiency within the system. So it turns out actually that salt is a terrific store of heat. It's been used in the concentrated solar industry now continuously for more than a decade. And so that certainly is the wisdom that we are using within our system. So in terms of combined heat and power, I think about it in two ways. So one is that our system generates heat on discharge. That is high quality heat that comes out around 120 degrees C. So that is very useful, for example, for district heating applications and certain kinds of, 100 to 150 degrees C industrial applications. Now, the hot salt is itself stored at 565 degrees C. So there's also the ability to top the heat store directly at that higher temperature. And the really interesting thing about CHP applications is actually the combination of electricity and heat. Certainly one improves the quality of the revenue to a project, but in addition to that, actually the ability to take renewable power and then create stored electricity and stored heat offers a way to decarbonize some industrial processes, which actually is a very difficult sector to decarbonize. And so absolutely, we're thinking about that. It's very much in our sweet spot.
Right on. Thanks. Gia, we had a question, I think, based on that first slide you showed about distributed hydro. Can you tell us more about what does it mean when we talk about distributed hydro? Where in the US or around the world is it being implemented? What are the barriers or challenges from moving from kind of dams and impoundments to distributed systems? And how might, that yield some kind of potential for kind of maybe interconnecting stuff that's not as large scale? I'm not sure.
Yeah, I'll unpack a few questions there. So I think that when we think distributed hydro, we generally view that as moving away from mega dams and mega projects. But in hydro, mega is like at a totally different scale. You're talking things that are like 5 gigawatts, 10 gigawatts, 20 gigawatts for some of the really large stuff, right? So distributed in hydro, starts to mean things that actually look like maybe hydro that was built before 1940, or and so you can still have projects that are quite substantial, 20, 30, 40, 50 megawatts type projects in size, in some cases bigger, but just where you're not building like, massive mega dams like necessarily have been built in the last couple decades. So that's one point. I think there, and then within that grounding, there's a range of, of interpretation, frankly, with respect to how, well, I'll just like there's another technical point. Are you putting that hydro into a distribution part of the grid or a transmission part of the grid? That's another nuance, which has an impact in terms of the interconnection process and how that hydro interacts with the grid in a specific way. In the US, I would actually say that there's quite a bit of hydro, again, old hydro that technically qualifies as distributed hydro. Like these are smaller projects, more distributed projects, not mega big dams. And so this is not something that's new. It's really actually in some ways looking back at what we were doing in hydro prior to building massive dams, and instead thinking about how we incorporate additional learnings, particularly in the last couple decades, around river restoration, dam removal, and certain types of new technologies, including ours, but others as well, on how we design those projects in ways that maintain river connectivity for fish, for sediment, for water, et cetera. And that's the other kind of nuance of not just doing more projects, but instead really focusing on how those projects interface with river connectivity. So I think, I think that answers it. It gets complex, but I think that's what when we talk distributed, those are the nuances that we go into. I think we're looking at a lot of existing examples, and then a lot of opportunity around actually thinking about how we improve the existing infrastructure that we have today to enable more hydro, leveraging existing infrastructure but do so in ways that also pay attention to the fact that all hydropower projects are water projects. Climate change is water change. How do we think about the multi-benefit elements of these projects in rivers?
Right. Excellent. Thank you. Ben, a quick question about how we should understand the reasonable limits or ranges of renewable penetration and how well we can really run large grid systems as those penetrations increase. I think the rule of thumb on these issues has been changing rather dramatically over the past 10 to 15 years, driven in large part by work from NREL and other DOE agencies on it. But how do you define the state of understanding of how much variable wind and solar energy the grid can take, and at what point those levels of penetration grow to the point where long duration energy storage and other technologies like that become absolutely critical?
Yep. So we definitely have seen a huge change in sort of that range of where people thought we could handle amounts of wind and solar. I remember a time, maybe not even 10 years ago, that people were like, well, we could never even get more than 2% variable generation into the grid. But as we've been working with small island power systems, we have demonstrated that we can run 100% wind and solar systems today. We have small power systems on small islands around the world that are operating with basically 100%. And when I say 100%, it's not only instantaneously, but all year long. As long as you put enough energy storage packaged with it, you can make those viable systems. And we're currently working with the Hawaiian Islands. So these are systems that are a little bit bigger. They're big island systems, but they have all the characteristics of a power grid: transmission, distribution, generation spread all over the island. They are up at 50% on Maui and Kauai, 50% on an annual basis with wind and solar. Again, we are adding a lot of energy storage into those systems. And critically, we're starting to use what we call grid forming inverter technology. So there are times during the middle of the day where they are 100% dependent on as we think about larger systems like the Texas system or the Western Interconnect of the United States, these systems will very shortly there will be times of the day where they will be a majority of them being operated from wind and solar and batteries all simultaneously running. And we're really pushing the limit here, where we think that we can get instantaneous levels above 70% if we start using grid forming inverters, all the way up to 100%. And that translates to over 50% annually from wind and solar. And then what we need to do is probably get close to 80% wind and solar on an annual basis for the most economic grid systems in the US. That still means that we're going to have hydro involved on this system and hopefully keep the nuclear plants around, but that could create this 100% clean electricity grid as fast as possible. But as you've heard, there are a variety of challenges on getting the storage issues worked out, making sure we have long-term storage available for these resources, and getting this stuff deployed will be critical. So.
Wonderful. Well, we do have a lot more questions, but I'm afraid we are out of time. But thank you so much. This has been a fascinating discussion. Gia, Ramya, and Ben, really appreciate your time and your expertise. And thanks again to Metcalf for hosting this conversation.
Thank you.
Thanks so much, Jeff. And to each of our panelists, Ben and Gia and Ramya, we really appreciate you all being here and sharing your expertise and insights with us on a very complicated series of challenges, but obviously a very important series of challenges. So thank you. And thanks to all of you who joined us today. We appreciate your attention. And don't forget, if you are excited by what you saw today and want to learn more and support these Metcalf Institute programs, please make a donation via the link in the chat. And we also hope that you'll join us for the final lecture in this series, which is going to be Sammy Roth of the Los Angeles Times, who will be speaking next Thursday at 1 p.m. Eastern Time. If you have not yet registered for that lecture, again, you can do that via metcalfinstitute.org. And we look forward to seeing you then. Thank you so much, everyone. Take care.
Thanks. Bye.